Perfect. So, in previous video, we saw something about non-idealities due to time scaling, right? And then we again realized um, our time interleaved sampling. So, in order to achieve a advance of t, here we use a filter. Let's say we use a filter so that we advanced for t, so that we can go for t samples instead of zero. So we can go for odd samples. So then this channel will go for even sampling, and this will go for odd sampling, right? Then we sampled it at the rate of 2t, then we upscaled it, and again we introduced a pole because we advanced this channel by t. So then again we have to get back to the original time instance, so we again introduced a delay of t. So uh, at this moment, when we are introducing a delay at this channel, uh, it's just one. So basically we are passing whatever. So we'll come through this terminology, that why are we introducing anything over here, because we need not to introduce anything over here while introducing over here. So we'll see when we go to n channels. So whatever the filter is over here we have, so it's basically the transfer function is one. So basically whatever the input is basically the output. So then in order to get the sampling at rate of t, we again stitch up the channels. So then we talked about sampling at n channels, right? So we can extend the same mathematics or same explanation for n channels, where we have basically filters whose transfer functions are h1, h2, and those are functions of frequency up to h of n. So what we here are doing is, so basically over here we laid the idea of advancing the signal by t for this channel in order to jump to the first orth sample. So then here we need not to do anything when it came to particular this case. But then when we have this case, so we have to consider a range of filters. Those are basically analysis filters in analog domain. So in order to achieve that sampling, and then we sample the signals, then we upscale them by n over here, and the sampling rate is nothing but fs by n when we talk about n channel sampling. Again, as we advanced over here, so we will introduce zeros over here to introduce, like, to get the delay covered, or the advance covered by the delay. We introduce a delay over here basically. So these filters are in discrete or digital domain, and they are called synthesis filters. And again, we stage them all up in such a way that the aliasing or the noise aliased cancels out each other through every filter, and we get the output as a sample of fs, sampling with a sampling rate of fs with zero noise ideally. So this is called the concept of multi-channel sampling, and the same mathematics is applied the way we talked about two-channel sampling. The same concepts are applied. So then, after covering the multi-channel sampling or time interleaved sampling, we arrive to the stage where we have to design a sampling circuit, right? So a sampling circuit is basically called sample and hold. Why sample and hold? So we will see it soon. So basically, to design this sampler, what we are doing, so we are going from, we have a continuous signal again, and we want discrete signal, right? Like this. So going from continuous domain to discrete domain. So we need sampling at the rate of discrete time t. So we basically need a switch, and along with a switch, we also need a capacitor to hold the charge. So then we have our input signal, which is a function of time, continuous in time basically. Then we have our switch and we have our capacitor to hold the charge when the switch is turning on and turning off. So then let's say we have an analog input, which looks like this, and we are sampling it at the rate of these samples. So basically we have our clock, and let's say when the clock is high, or the half first of like the half cycle of clock, we are measuring or taking the input and turning the switch on, and in the second half of the clock we are turning the switch off. So let's say the switch is closed for one half of the clock period, and it is open for the other half of the clock period. um, it looks like this. So what we are doing is we have our clock, which is representing our sampling frequency, basically, or the time t. So then we have our signal like this, right? So as we said, the switch is closed. So this switch will be closed in the one half of the clock period. So then it will track. So the when the switch is closed, the input is uh, getting sampled on capacitor. So it is tracking the input. So for this range, it is tracking the input. Again, when the switch is open for the second half, it is holding. So basically it is holding and it is not tracking. So whatever the input voltage has been sampled on capacitor, so when the switch is open now, so capacitor will hold a value, it will hold the voltage which it was imposed on when the switch was closed. So suddenly when the switch is open, so now the capacitor has the sample which is held on the capacitor. So then it will hold for that period of time. Again, let's say as of now the switch is ideal, so it will again turn on. So then it will jump. So we hold here, then we again uh, jump, and the switch will like the switch is closed again, so it will start tracking again. So then it will track again for that half. Then again for next other half of the clock, it will again hold, and when the switch is again closed, it will again start jump to the signal and it will start tracking. So then again it will track, then it will hold, again track. So basically this is how we are sampling. So that's why it's called track and hold sampler, where we track for half of the cycle and we track hold for half of the cycle. So basically for this half, when we are tracking, the switch is closed, and when we are holding, the switch is open, and the transition between open and close, so we are considering ideal over here. So that's how we are getting, we are able to track and hold when we consider the jumping is ideal. But we know in reality, the time constant for a capacitor to charge or discharge, or basically to switch up or switch down, is RC time constant. So we'll come to it. So this is what we talked ideally, right, about tracking and holding. So that's how we are sampling our signal. But there are non-idealities in such circuits. So first is we need to switch. We need a switch, right? So the switch can be controlled by some signal, and uh, the switch need to be uh, turned on and off. So a switch ideally is nothing but when the switch is on, we say that there is a short circuit. So everything flows without seeing any resistance. But in reality, there do exist some resistance associated with a switch. So basically that resistance can be shown by R on. So when we switch on the circuit, so ideally we say that it's a short circuit, but it's not a short circuit, but there is a resistance associated with the switch, which is R on. And now when we look at the circuit, so we have our Vn, which is a continuous time signal with amplitude A. So it's A cos omega t. And we have a RC circuit. So what is the RC circuit? So basically it's a basic RC filter, and at this point we are taking the output. So our output will be nothing but the output of a RC filter. So our signal is being passed through a RC filter. So our transfer function basically will look like, or basically our output will look like A cos omega t minus phi. So this is the phase introduced by the filter divided by under root 1 plus omega square r square c square. So this is a typical transfer function of basic RC circuit or a basic RC node, and the voltage is taken from this node. So, and this phi is basically nothing but tan inverse of omega r and c. So this is the non-ideality we are talking about. Ideally, we were expecting the output to be A cos omega t, right? Because this is the input. But then we are again there with non-idealities, which is a phase lag of phi. And in the denominator, we have this thing due to the RC node. So then in order to get V naught as much as possible as V in, so basically in order to get V naught resemble with V in, we need basically this entity to be very, very less than 1, so that this value will be very close to 1, and root 1 is basically 1. So our V naught will be basically A cos omega t minus 5, and that's how it will resemble with Vn. So we need this entity to be very, very small than 1. So which means we need omega n to be very, very small, or basically when we talk about frequency to be very small, so time period to be very large. So that's how we say that the time period of the input signal should be very large. But in respect to what? So when we say that omega n r on c is should be very, very less than 1, so basically RC should be very, very less than 1 also, right? So when we like transfer this omega n over here, so RC should be very, very less than 1 upon omega n. So 1 upon omega n is basically the time period of the input signal, and RC is the time constant for that capacitor basically. So this means the input time period must be very, very larger than the RC time constant of the circuit itself. And also 1 upon RC is the bandwidth of the RC filter, right? So 1 upon RC during the tracking phase is basically the bandwidth during the tracking phase when the switch is off. And in order to have a good tracking bandwidth, we need to make sure that RC is very small in order to get this quantity very high, as we need a very good bandwidth. So now when it comes to the selection of RC value, so until now we understood that okay, so there do exist the non-ideal R on, so it turns out to be a RC circuit. So we have a bandwidth. So we talked that our input time period should be very, very greater than RC, or basically our 1 upon RC value should be very good, or in a appropriate manner. So in order to have a very good tracking bandwidth, our RC should be very small. So then our RC should 1 hour RC should be small. So when it comes to selection of RC values, so we can take R into C according to our circuit, or else we can take R by 2 times 2C. This will also satisfy the same thing. Or we can take 10R multiplied by C by 10. So this will also satisfy the same condition. So then when all of these things will give us the same RC time constant, then which combination should be chosen between these? So to discuss this question, we need to discuss the concept of uh, the second non-ideality, which is the noise associated with the resistor. So when we use the resistor or R on, so every resistor comes with its own noise, and it is represented by a voltage which is in series. So it is represented by a voltage source in series or a current source in parallel. So in for the sake of easy calculation, we will take voltage source in series with that R on in order to represent the noise in that resistor. So Vn is basically a noise, and the mean value of that noise is basically zero. So the noise is always considered in spectral density. So the spectral density of this noise is nothing but 4 kT/R on. So these concepts, like you can, I have talked about this concept in very detail in the playlist of analog IC design. So you can please refer to that playlist. So basically, talking about the spectral density. So this K is Boltzmann constant, and this T is absolute temperature in Kelvin, which is 300 Kelvin at room temperature. And this is our on. So the spectral density is given in the terms of voltage square per hertz. And basically, what does spectral density means? So it represents the power of that noise. In what sense? So let's say we have a register and its noise is represented by a series voltage source. So if we take that register and monitor the voltage across it using let's say a oscilloscope, so we would see some random waveform, and if we filter that random waveform with or through a ideal band pass filter with a bandwidth of 1 kilohertz. So let's say the center frequency is f naught, any f naught. So there will be some waveform at the output of the filter with the mean squared value, which will be 4 kT/R. So this is what it means. So what we are saying that we take this resistor and we measure its two ends. So when there is no input, so we are basically measuring the two ends. There is no external add-on input. So then it will show a random waveform along, like it's basically with a zero mean. But when we have a random waveform, so what we will do, we will have a band pass filter with, let's say, the center frequency is, let's say we have a band pass filter and the center frequency is let's say f naught. So this is the f naught central frequency, and it will take a bandwidth of 1 kilohertz. So for that 1 kilohertz bandwidth and center frequency f naught, there will be the output whose mean squared value will be 4 kTR. So that's what spectral density means. Also, regardless of f naught, so whatever the central frequency is, until and unless the bandwidth is 1 kilohertz, the spectral density or the mean squared value remains 4 kTR. So it is independent of the center frequency. So if we are getting along the range of frequency, we are getting that noise. So take any bandwidth, take any bandwidth of 1 kilohertz, regardless of whatever the frequency is. So we consider the center frequency over here, and we consider the bandwidth of 1 kilohertz over here. Again, we will get the same spectral density. Consider it over here, same, until and unless the bandwidth is 1 kilohertz. It is independent of center frequency f naught. So that's how it works, and that's what the spectral density is. So basically, the input which drives the band pass filter has a strength which is independent of frequency, and the band pass filter is just taking all frequencies around f naught, basically the around center frequency, which is up to 1 kilohertz. But regardless of any value of f naught, so as I mentioned, we can take f naught anywhere, regardless the value of f naught, the mean squared value is same for any f naught, and such noise is basically called as white noise. So let's see what happens when we use or when we when we are in a track phase and the input is 0. So we have a track phase, we have a hold phase. Again, we have a track phase, we have a hold phase. So when we are in a track phase for half of the clock cycle, so in that phase, when the input is grounded, so basically when the input is 0, there only exists the switch which is turned off. So when the switch is turned off, we have R on, and this R on has its noise, which is represented by Vn in series, and we have our capacitor. So there is no input as of now. Still, due to Vn, the V naught is basically, so at V naught, we are basically getting a low pass filtered version of noise. So RC is acting as a low pass filter, and the noise is being getting filtered. And at this node, the output node, we are basically getting a low pass filtered version of the noise. So now suddenly, when we are opening the switch, so when we are closing the Vn, so basically something is getting sampled on C. So C has been charged, and when we suddenly open, uh, what happens to the output? So when we go from the track phase to the hold phase, so the voltage, whatever it was on capacitor, let's say across capacitor, so basically that's the same voltage as at this node. So whatever it was at this instance will be held by the capacitor. So given that the mean value of Vn is 0, so the held voltage will also have a mean value of 0. But given when we suddenly open the switch, so what happens is whatever existed, so whatever voltage existed at this node before opening the switch is basically what is stored in the capacitor. So the mean squared value of the voltage sampled on the capacitor, so basically what is stored on the capacitor is basically what is sampled on the capacitor. So the mean squared value of that sampled voltage on capacitor is just simply equals to the mean squared value of the voltage waveform that was across the capacitor when the switch was closed. So that's how it is. So what is mean squared value of noise sampled on the capacitor? So that's our focus. So basically, what's that mean squared value of V naught, or basically the sampled mean squared value at capacitor? So we said that we have RC network, right? So basically, this is a RC filter. We can consider it as a RC filter, and it has its own transfer function. So we have an input to this RC network and we have output to this RC network. So we represent this RC network with a transfer function of h of f. So at the input, we have SVN. So basically we have noise whose spectral density is 4 kTr on, and we have our output. So the spectral density of our output voltage will be nothing but the power or the spectral density which is present at the input times the square of the magnitude of the transfer function. So that's how we'll get the spectral density at the output. So even though the spectral density SVN at the input is independent of frequency f naught, but the system is dependent of the frequency as it's low pass filter. So the magnitude of h of f is nothing but 1 upon 1 plus the square of 2 pi f r on c. So this is the magnitude of the transfer function, and as we have seen that transfer function, so this is the transfer function basically. So this is the magnitude of that transfer function, and when we square this magnitude and multiply it with the spectral density of the input, so what we get as a output spectral density, So this is what we get as an output spectral density. Hence, when we had an input noise source with a power which was uniform as a function of frequency. So this was uniform as a function of frequency, and we pass that to a filter whose gain is not uniform. It's varying as a function of frequency. Hence, the output power will be input power times the square of gain of that frequency. So then we will analyze this. So basically, we will analyze this on a Bode plot. So this is in log scale. So this is the magnitude, and this is also in a log scale, and this is representing omega. So initially, what we say that at DC, basically, when the presence of capacitor is very less. So at DC, or at very low frequencies, let's say at zero frequencies, we have Fs0. So this whole term is zero. So we are remaining with the DC term or the DC magnitude, which is 4 kTr. So at DC, we have 4 kTr. So we start with 4 kTr. And as the dominance of pole increases, so basically pole is where the capacitance and the resistance are dominating or contributing equally. So at this point, we are getting half of the value. So now after the pole, the low pass filter acts as and gives us maximum attenuation. So the filter is basically selectively letting the low frequency components of the SVN or the spectral density of the input pass through it, and the mean squared value of the voltage or the noise which is sampled on the capacitor can be given by V square, which is nothing but integral of the output spectral density to df. So when we integrate to in order to get the mean squared value of the sampled voltage on the capacitor, so basically uh, we integrate this value. So when we integrate this value with respect to df, and when we solve this integration, we get our mean squared value to be kt by c, and surprisingly it is again independent of r. So how is this independent of r? So basically this root mean squared value is the area lying under this curve. So we have r over here also and r over here also. So basically this is representing the bandwidth and this is representing the amplitude. So when if let's say if the amplitude decreases, so when the amplitude decreases, the bandwidth increases, and this curve, if the amplitude decreases, this curve looks like this. So again, regardless of r, the area under this curve remains same. So this area was the same as when we increase the bandwidth and decrease the amplitude. So the function is derived, the transfer function is basically the Bode plot is derived from this function. So go through this function in detail, so you'll understand that it is the output is independent of R on. So if we take a track and hold with zero input, and the switch can have an arbitrary resistance R on, and because of the noise associated with R on, when we open the switch, so basically when we go from track phase to hold phase, the voltage stored on the capacitor is some random voltage due to noise, and the mean square value of that random voltage is nothing but kt by c. Hence, when we have Vn along with us, so now we also have Vn. So basically, this is what we are trying to achieve, right? And this is how our ideal switch looks like. So at the output, we have the sampled Vn with the frequency 1 by Ts, or basically the time sampling time is Ts. Along with that, we also have something due to noise, and this has a RMS or mean squared value as kt by c. So this portrays that while sampling, the output is already corrupted due to the non-ideality of switch. But to what extent is it corrupted? Because yeah, okay, there are non-idealities, but to what extent? So that is decided by this KT by C, and that's why in order to have the minimum extent of non-ideality, we need the denominator C to be high, and that's how we arrive to our question again. So then which combination will we choose? So we'll choose basically the one which offers maximum capacitance in order to have a minimum extent of non-ideality in our output. So that's all for this video. Now, if you have any doubts, please ask. So now, if you are having doubts regarding RC network, so you need to go through the transfer function. So what is basic RC filter? So Sneha might be aware due to AMCD. So maybe Sneha can share the resources to Hania to go through RC filter, or basically to go through the analysis of RC filter. Or basically we have this transfer function, right? So how do we plot on a Bode plot? So this will be covered in the basics of RC filter. So if you guys have doubt, then please ask.